Furthest forward.
Want to go old school? How about this?
On-off switch on the side. Yoshi. It's on-off switch on the side. It's not working. It's not working? No.
Okay.
Okay. So
my talk devoted to some theoretical results about turbulent helicity and its realization, atmospheric flows, and its yes, I see, I know. So when Evgeny Novikov wrote in the beginning of the 70s a paper devoted to theoretical investigation of the vorticity flux tensor, he write only non-diagonal components of this tensor. In the beginning of the 70s, the conception of helicity and turbulence yes. In the beginning of the 70s, the conception of turbulent helicity is not so he considered only non-diagonal terms of tensor. And if he considers the diagonal, he can talk about he can describe helicity, but the conception of helicity started in the 70s with Moreau and Moffat. Helicity introduced as a integral of the scalar product of velocity and vorticity vectors. If we consider the Euler equations, we see that the present in vertical form, we see the present of helicity. The sum of path of flow leads to reduction of nonlinearity, and so consequently, it is the diminishing of the large of the direct transfer energy from large to small scales. So, from helicity, it's known the conception of helicity cascades. There is direct cascades, parallel cascades of helicity and energy from large to small scales, and also is known the inverse cascades of energy and the inverse cascades of energy and to large scales, and direct cascades of helicity to small scales. Such situations is discussable. You know. Here it is eta it is dissipation of helicity, epsilon is energy dissipation. Theoretical consideration of helicity is in the works of Brissot, Kuznetsov, Moiseev, and other. There is one of the first numerical models of helicity, Andrel and Lagier, and other papers, interesting papers with Chin, Borot, Underzai, Poquet, and many papers of Poquet and Menin in the in the last decade. Laboratory experiment of helicity is known with the group of Zinnober in Israel and Wallace in Maryland. The first, we suppose, the first atmospheric boundary layer measurement of helicity made in the Institute of Atmospheric Physics in Moscow by the group of Prof in the beginning of the 80s. From the helicity, we know the exact relation connected the some components of the third correlation tensor with the dissipation of helicity. It's so call it 2/15 law. Its law is similar to well-known falsified law for usual triple correlations. This law have some have some evidence in numerical simulations, shell models and direct numerical simulations. From this if we write this tensor, we can see that such tensor where is the component of velocity, two components of velocity in one point, and another component of vorticity is a second point. Such tensor will be non-zero and have some components. So we can expect f-1 dependence in the frequency spectra of turbulence. So we know in numerical experiments well known the generation of different sign helicity structures. The interest to atmospheric measure of helicity connected also with large scale dynamics. It's known that helical properties of turbulence may change the structure of Reynolds strength tensor and affect on large scale dynamics and stability criteria. It should be noted the papers of Moiseev and co-authors started in the beginning of the 80s. Works of Levich and co-authors in the beginning of the 80s. Some papers, Kurgansky, Ponomarev and others. Also is known subhead helicity parameterizations. So it's interesting to see the values of helicity for atmospheric structures. This is from a paper of Chizhelsky. We see that helicity is a dimension of gravity accelerations. Meters per second minus 2 is the helicity of hurricane, the helicity of rotating storm, helicity of tornado. Helicity of Heckman layer is 10 minus 1. So helicity of atmospheric boundary laws is boundary layer rolls approximately 10 minus 2, 10 minus 3. One of the examples of one of the bright examples of the helical structure atmospheric boundary layer, it is roll circulations, quasi two-dimensional motions. It is the Baltic Sea, well known. It is the Barents Sea, Okhotskaya Sea. It is the structure of these circulations. So if we consider helicity balance and atmospheric boundary layer, we see the next. Omega it is the coronal velocity. It is stress, turbulent stresses. We see that in the temperature due to temperature stratification, we see the another helicity source. Consider with the mutual correlation with temperature fluctuations and vertical velocity fluctuations. After some calculations, we can obtain an estimate for helicity, where helicity is connected with the turbulent viscosity and superhelicity of large-scale flow. And if we and for this and we can obtain for helicity, turbulent helicity atmospheric boundary layer, such values, 3 and 10 minus 3 and 2 10 minus 10 minus 2. It should be noted that this values of helicity is very close to the helicity atmospheric boundary rows circulations. If we want to measure the helicity, we need to measure the vorticity. Well-known direct measurements of vorticity. It's connected with hot wire arrays technique. From these papers, I note the paper Holmianska and Zinnober. They measure helicity with atmospheric boundary layer. Very interesting papers. However, there is indirect vorticity measurements connected with circulation measurements in atmosphere and oceans, based on acoustic method. It is we measure the circulations on the contour and can obtain vorticity on this contour. The base of the contour, from several centimeters up to several meters. Such method also developed in ocean turbulence investigations. Here is the principal scheme of the circulator scheme developed in Institute of Atmospheric Physics in Moscow. It is 2 transmitters, two receivers with different frequencies, and the signal transit time contains velocity circulations or phase difference. It is this circulator mounted on the mast with height 45 meters. Also, here is simultaneous measurements of velocity components with acoustic anemometer. It is an example of 2-component circulator. The red color is correlations of the components of the components of measured velocities, temperature, and circulations. We see that mutual correlations of the horizontal component of velocity circulations is non-zero, good non-zero values from unstable stratification and stable stratifications. Here is the entropy spectra. Here we see the day-night helicity spectra. We see that he is very close to parallel cascade, minus 5.3. It is the helicity fluctuation spectra according which close to minus 1.3. It is estimation from the Kolmogorov theory from these fluctuations. It's a typical realization of circulation fluctuations. It is circulations probability density functions. It's detail details of the helicity probability density function. We see that typical non-Gaussian character. We see details in the logarithmic scales, closer to exponent. Yes. And the questions that we discussed, the dependence from the three components tensor from two components, velocity and vorticity. And we see from different daily data. We see from different components the dependence closer to -1. This it is the noon time. So it's so the same data beginning in the evening, close to evening, also close to -1. And it is the night observations of the oscillations in velocity, and we see not so good, no, but also close to -1 character for this fluctuation. So we did an experimental technique for circulation vorticity measurements. Atmospheric boundary length has been developed. The turbulent helicity values atmospheric boundary layer are in correspondence with theoretical estimations. Approximately experimental estimates of the atmospheric boundary layer give the helicity spectrum slope about -5.3 that corresponds to the helicity transfer towards small scales. Distribution of helicity have appreciable asymmetry and non-Gaussian character. And spectrum slope for the triple two-point correlations and helicity vorticity correlations is close to very f-1. It's the first experiment evidence for 215 slope for helicity cascade. So the authors are thanks to Генрих Хадидян, Вячеслав Безверхний, Георгий Голицын, Evgeny Glever for fruitful discussions and help. So, thank you.
I'm sorry again, I didn't mention the title of the paper, Turbulent vorticity and the helicity in stratified atmospheric boundary. So now the time for questions.
You quote helicity in dimensional form, in terms of meters per second squared.
Yes.
What really would be interesting would be to have it either normalized with respect to U and omega, as was done in the previous paper, to get a dimensionless number, or even compared with the energy. Then there's an upper bound on helicity, theoretical upper bound, when compared with compared with the energy and the dominant length scale.
Yes, it's from this data. It scales. It scales 50 and 100 meters of this data. We do an estimate for this from this data, and the scales which can obtain from energy and helicity is approximately from 50 to 100 meters.
Mm-hmm.
It's close to the characteristic scales of the atmospheric boundary layer circulations, the vertical scales of the circulations. Approximately 200 meters. So it's interesting that the value of turbulent helicity is close to the is close to the helicity values of the atmospheric boundary layer rolls. So I see that it is the elements of one simultaneous cascade from large to small scales.
Any other? Does circulimeter you mentioned?
The first circulation matter. The first circulation matter. This circulation matter is diameter 1 meter. 1 meter. So we can measure the atmospheric turbulent circulation from 10 meters. It would.
Oh, okay.
From 10 meters and out. Great.
So it's measuring velocity difference, or can you somehow calculate the vorticity directly, or?
We calculate vorticity. We measure the circulation on this contour and hence obtain vorticity.
I see.
According to the theorem of circulation.
Any other questions? If not, so thank you.